We have been everywhere. Mars has been crossed by rover wheels. Pluto was photographed from less than 13,000 kilometers away. A probe was dropped through the clouds of Saturn and kept transmitting almost all the way down. In 60 years of spaceflight, we have visited every planet in the solar system. Crossing billions of miles of empty space has started to feel almost routine. But there is one direction we have barely touched, straight up, perpendicular to the flat disk where all the planets orbit, directly above the Sun's north pole, or directly below its south. It sounds simple. Point the rocket up and go. But physics will not allow it. Over the next 13 minutes you will understand why. Why reaching a point directly above the Sun requires more energy than reaching Pluto. What is hiding in those unexplored regions? And why the only realistic way to finally escape upward is to first fall inward toward the Sun itself. Here is a fact that most people never truly internalize. Right now, while you are watching this, you are flying. Earth moves around the Sun at 30 kilometers per second. That is not an approximation. Every single second, the ground beneath your feet travels 30 kilometers sideways through space. For context, a bullet from a high-powered rifle travels about 30 times slower than the planet you are standing on. Every rocket we launch inherits that velocity. Before a single engine fires, every spacecraft is already moving sideways at 30 kilometers per second. This is normally an enormous gift. When we want to reach Mars or Jupiter, both sitting in the same orbital plane, that sideways momentum does most of the work. A small adjustment in the right direction, and you are already on your way. But what happens when you want to go up? Not sideways toward another planet, straight up, perpendicular to everything else. Those 30 kilometers per second become a wall. Aerospace engineers measure mission cost in a value called delta V, the change in velocity a spacecraft must produce entirely on its own. Think of it as the true price of a mission, paid in physics. Compare the numbers. Reaching Mars from Earth orbit, roughly 4 kilometers per second. Reaching Jupiter, roughly 6 kilometers per second. Reaching Pluto, roughly 11 to 12 kilometers per second. Escaping straight up out of the plane of the planets, roughly 30 kilometers per second. You heard that correctly, a destination that is many times closer than Pluto in terms of raw distance requires nearly 3 times more energy to reach. The reason is that sideways orbital velocity. To travel perpendicular to the plane, you must first completely cancel 30 kilometers per second of lateral motion, and then accelerate upward from zero. It is like trying to swim directly across a powerful river. Swimming with the current, or even at a slight angle, is easy. Swimming straight across costs you everything. Orbital mechanics gives us free speed in one direction, and that is precisely what makes every other direction so expensive. We have maps of Mars with individual boulder resolution. We have seen geysers on Enceladus, storms on Jupiter, mountains on Pluto standing 3 kilometers tall. Now look at this. This is the south pole of our Sun, the closest star to Earth, the object that makes life on this planet possible. This image was captured for the first time in 2025. Until last year, no human and no machine had ever seen what the top or bottom of our own Sun actually looks like. Not really, not from above. Why does this matter beyond the novelty? Because the polar regions of the Sun are where the most important solar activity originates. The fastest solar winds stream outward from there. The Sun's magnetic field reverses every 11 years through processes that begin at the poles. The entire space weather environment of our solar system is driven by what happens above and below the solar equator, and we have been studying it almost entirely from the side. like trying to understand a hurricane by standing at the equator and watching the clouds go by. In 1990, NASA and ESA found the only available escape route from the trap. If you cannot go straight up, you go around. The Ulysses probe did not fly toward the Sun. It flew in the opposite direction, out to Jupiter. Using the gas giant's gravity as a slingshot, the spacecraft bent its orbital plane by nearly 80 degrees relative to the ecliptic. It was an elegant workaround. You cannot overpower physics directly, but you can use its own tools against it. Ulysses gave us the first direct measurements of fast solar wind streaming from the polar coronal holes. For the first time, scientists were sampling the Sun's poles directly, not inferring them from indirect data. But there was one critical limitation. Ulysses carried no cameras capable of imaging the poles. Built on 1980s technology, it could measure the environment, but it could not see it. We got the data. We never got the picture. In 2020, ESA launched a new probe, Solar Orbiter, this time with cameras. Rather than one dramatic gravity-assist at Jupiter, Solar Orbiter uses a series of repeated Venus flybys, gradually, orbit by orbit, tilting its trajectory steeper and steeper. Like spinning a coin on a table, each rotation shifts the angle slightly further. In March 2025, the first images arrived, a chaotic, magnetically tangled region. Nothing like the smooth, uniform surface we see from Earth. An entire world sitting right above us that has existed for 5 billion years and that we are only now seeing for the first time. This was humanity's first genuine top-down view of a solar pole. Not approximate, not sideways, real. And Solar Orbiter is still climbing. Its orbit is still tilting. The best images are yet to come. Surrounding the Sun, there is an enormous structure called the heliosphere. It is the region of space where the solar wind dominates, pushing back against the interstellar medium beyond it. Inside this bubble live all the planets, all the comets, and every spacecraft humanity has ever launched. Outside lies the galactic environment, saturated with cosmic rays that this bubble shields us from. For decades, the standard model showed the heliosphere shaped like a comet, a rounded front pushing into the direction of the solar system's galactic motion, and a long tail stretching behind. It was logical, it was clean, and it may be entirely wrong, because we have never seen it from outside. In 2020, a team led by Merav Ofer at Boston University published a new model built on NASA observational data. The result surprised the field. The heliosphere, according to this model, does not look like a comet at all. It looks more like a deflated croissant, a rounded central volume with two short curving jets extending outward, and no long tail. Why are we still not certain which is correct? Because both Voyager spacecraft, the only probes ever to cross the heliospheric boundary, did so traveling almost entirely within the plane of the planets, a lateral cross-section, valuable but incomplete. It is like trying to determine the shape of a balloon by poking a single needle through its middle. To understand the true shape of our home in the galaxy, we need a spacecraft that climbs well above the plane and looks back down. A vantage point no probe has ever reached, for a structure we live inside without knowing what it actually looks like. The problem is defined. We need an escape from the planetary plane. But the 30 kilometers per second wall has not moved. Simply building a larger rocket is not the answer. The propellant mass required for a direct vertical escape exceeds anything a realistic launch vehicle could carry. The rocket equation punishes you. The more fuel you add, the more fuel you need to lift that fuel. The solution is counterintuitive. Instead of flying up, you first fly down, toward the Sun. Imagine a spacecraft released toward the Sun, accelerating under solar gravity. At its closest approach, at perihelion, it is moving at over 100 kilometers per second. And at exactly that moment, the engines fire. This technique is called the Oberth maneuver, named for German physicist Hermann Oberth, who described the underlying principle in 1929. The logic is this: a rocket engine is dramatically more efficient when the spacecraft is moving fast and sitting deep in a gravitational well. The same quantity of propellant burned at perihelion delivers far more orbital energy than the same burn performed in open space far from the Sun. In practice, the spacecraft falls toward the Sun, accelerates to hundreds of kilometers per second, fires its engines at the point of closest approach, and launches vertically out of the solar system's plane like a stone from a sling. The closer to the Sun at perihelion, the more powerful the effect. Some mission architectures propose a perihelion as close as 3 to 4 solar radii from the surface of the star itself. The fall becomes the launch pad. There is a second approach, slower, more patient, arguably more elegant. A solar sail, an enormous sheet of reflective metallic film, thousands of square meters across, uses the pressure of sunlight itself for propulsion. No fuel, no combustion, just photons pushing against a thin surface. A solar sail cannot accelerate a spacecraft quickly, but it never stops pushing. Week after week, month after month, that gentle pressure slowly tilts the orbit steeper and steeper. Now combine the two approaches. A solar sail slowly spirals the spacecraft inward, closer and closer to the Sun over the course of months. At maximum proximity, the engines fire. The Oberth maneuver throws the probe vertically out of the plane. The sail then continues working, helping sustain the climb into the polar regions above the Sun. This is the mission architecture that astrodynamicists today consider most credible. Not theoretical, actual engineering proposals, actual trajectory calculations from actual space agencies. If the mission succeeds, what does the spacecraft actually observe? First, clarity. The plane of the planets is filled with dust, remnants of billions of years of asteroid collisions and cometary debris. This dust produces the zodiacal light, that faint pyramid of glow visible before dawn or after dusk on dark nights. It is the interior of our own solar system, illuminated. A spacecraft climbing above the plane would leave this dust behind within months. The view from there is dramatically cleaner. A telescope operating from that position could detect faint signals from distant star systems that are currently drowned out by local haze, making it potentially one of the best positions from which to search for biosignatures around other stars. Second, a different solar wind. Above the Sun's equator, the slow solar wind blows, roughly 400 kilometers per second of turbulent, dense plasma. Above the polar coronal holes, a faster and smoother stream emerges, 700 to 800 kilometers per second of particles flowing outward in a thinner current. A spacecraft passing through this environment would experience fundamentally different radiation conditions, with real implications for both instrument survival and the quality of science returned. Third, the view of our own neighborhood. For the first time in history, a real photograph of the solar system from above. The disk of the planets, the dust plane, the heliosphere in whatever shape it actually turns out to have. We have seen the Earth from orbit. We have photographed galaxies billions of light years away. But a true top-down image of our own solar system does not exist. Not yet. 2 paths, 1 destination. The solar sail, slow, patient, propellant-free. Years of spiraling, the Sun itself serving as the engine. The spacecraft does not hurry, but it never stops. The Oberth maneuver, fast, dramatic, and unforgiving. A controlled fall toward the surface of a star. A precise engine burn in conditions of extreme heat and radiation. Then a vertical launch out of the plane at speeds no spacecraft has ever reached. Both are physically real. Both are technically justified. Both require solving engineering problems we have not fully solved yet. But either path leads to the same place, above our solar system, to a view no instrument has ever captured, to measurements that do not yet exist, to answers for questions we cannot even ask correctly yet, because we have never looked from that angle. We have conquered heights. We have crossed oceans. We have reached other worlds. One direction remains: straight up. If you want to know what is actually waiting up there, in the space directly above and below the disk of our planets, that is what the next video covers. This one told you about the journey. The next one shows you the destination.